All of physics is either impossible or trivial. It is impossible until you understand it, and then it becomes trivial. In this video, we will have a discussion on Weizsacker's semi-empirical mass formula. Weizsacker's semi-empirical mass formula was proposed by Carl von Friedrich Weizsacker in 1935. He proposed his mass formula based on some experimental results and partly on assumption. That's why this mass formula is called as semi-empirical, partly on experiment results and partly on some logical assumptions. And he gave this mass formula completely based on or taking into account the liquid drop model of the nucleus. We all know if a nucleus have Z protons and N neutrons, we can calculate the nuclear mass as Z times the mass of the proton plus N times the mass of the neutron, where Z stands for the atomic number, that is the number of protons present inside the nucleus, and MP the mass of the proton, and N is the number of neutrons in the nucleus, and Mn is the mass of the neutron. But when you weigh a nucleus by a mass spectrometer, we can find the actual mass will not account for the calculated mass calculated using the above formula. So where does this mass discrepancy comes? So this mass discrepancy or the loss in the mass appears as the binding energy, which can be calculated according to Einstein's mass energy relation E equal to mc square. So we can write the corrected mass as M is equal to the corrected mass capital M is equal to Z times mp plus N times mn minus Eb by c square, where this Eb is the binding energy of the nucleus. But the binding energy in turn depends upon the following terms: the volume energy term, surface energy term, Coulomb energy term, asymmetry term, and pairing term. All these 5 terms contribute greatly to the binding energy of the nucleus. Volume energy term. This volume energy term enhances the binding energy of the nucleus, and this volume energy arises because of the strong nature of the nuclear force existing in the nucleus. We all know nuclear force is the strongest force existing in the universe. So this binding energy depends greatly on the size of the nucleus, so which in turn is proportional to the volume of the nucleus. So if the volume of the nucleus is more, it can occupy more number of nucleons. So the larger the value of A, more the binding energy. So we can write the binding energy is proportional to volume of the nucleus. So the volume of the nucleus, since a nucleus is spherical in shape, we can write the volume as 4 by 3 pi r cube. We know the radius of the nucleus is given by r naught, r is equal to r naught a power 1 by 3. Substituting in that, we get 4 by 3 pi r naught cube into a, or in general writing the constants by av, we have eb is equal to av into a. So where this av is nothing but the constants 4 by 3 pi r naught power 3. So look at the diagram. One nucleon is surrounded by 5 nucleons. So if it is surrounded by 5 nucleons, the attractive nuclear forces will be greater. So more the number of nucleons, more is the binding energy, part due to the volume energy. The second contribution comes from the surface energy. So there will be some nucleons present on the surface of the nucleus. So they are loosely bounded, they are partly bounded to the nucleons inside. So this surface energy arises due to the nucleons present in the surface of the nucleus. So this surface nucleons will try to decrease the binding energy of the nucleus, and this is greatly observed in lighter nucleus. So for example, if you take helium, so there will be only 4 nucleons. So the 4 nucleons will be only in the outer surface. So this outer surface nucleon will try to destabilize the nuclei. So the surface area can be given for a spherical nucleus can be given by 4 pi r square. So the binding energy is proportional to 4 pi r square. Writing r naught a power 1 by 3 in place of r, we get 4 pi r naught square a power 2 by 3, or you can write it as EB is equal to minus AS a power 2 by 3. So the negative sign is introduced here because the surface energy term tries to destabilize the nucleus or decreases the binding energy of the nucleus. The third contribution comes from the Coulomb energy term. We all know what is the Coulomb energy. So a Coulomb energy or the Coulomb force means the force of attraction or the energy between the two protons or the neutrons. So this arises due to the electrostatic repulsion between the protons present inside the nucleus. We all know the protons are the positively charged ions, and this positively charged ions cannot stay together. Since both are highly positive, they will try to repel each other. So this Coulombic force also decreases the binding energy of the nucleus. So in general, the electrostatic energy of the nucleus E is given by 3 by 5 1 by 4 pi epsilon naught q square by r. In case that particular nucleus has z protons and z minus 1 proton pair, so you can write z into z minus 1 in place of q square, and replacing capital R is equal to r naught a power 1 by 3, we get EB is equal to, writing all the constant terms by means of a constant AC, we get minus AC z into z minus 1 divided by a power 1 by 3. So in the diagram you could see the red pairs are nothing but they are the protons. So the electrostatic repulsion existing between the protons will try to destabilize the the nucleus. So next asymmetry term. So this asymmetry term arises, or the contribution for the asymmetry time arises due to the lack of symmetry. So in lighter nuclei, the number of neutron and proton is almost equal. If n is equal to z, that is the number of neutron is equal to the number of proton, the stability of the nucleus is more. But when you go higher up the order, the number of neutron exceeds the number of proton, hence asymmetry results there. So n minus z asymmetry results there. So we can write EB is equal to minus a minus 2z the whole per square by a. See, in the diagram we could see a proton neutron pair, and 4 neutrons are there without any pair. So the asymmetry between the number of protons and neutron arises there. Because of this, we get this asymmetry energy term, and this asymmetry energy term also try to decrease the binding energy of the nucleus. And the fifth contribution comes from the pairing term. This pairing term energy arises due to the pairing of the nucleons of the same type with opposite spins. So in the diagram you could see a proton-proton is linked, a neutron-neutron is linked. So a proton-proton can be linked, but these two protons may not have a same spin. So a nuclei with even Z and even N are found to be more stable than the odd Z and odd number of neutrons. So a correction term is introduced here, which is named by delta, and this delta is positive for even pair, and it is negative for odd pair, and it is 0 for even odd pair. So if you have even Z and even N, so delta will be a positive number. If you have an odd Z and odd N, it is negative, and if you have odd N and even Z, or even N and odd Z, the delta goes to 0. So we can write the pairing energy term, the binding energy contribution from the pairing energy term is equal to plus or minus del into Az. So the binding energy of the nucleus can be then represented by including all the contribution from the 5 terms as AV capital A minus AS A power 2 by 3 minus AC Z into Z minus 1 by A power 1 by 3 minus AA A minus 2Z by A minus 2Z the whole square by A plus or minus del into del AZ. So the values for the constants AV, AC, AA, del can be given by. So these are the best values obtained from the various experiments. So what are the merits and demerits of this Weizsacker semi-empirical formula? So this formula explains the stability of the nucleus in a better way, and we can apply this formula to heavier nucleus, and it gives very good results, but still it lacks some goodness, and this failed to explain the magic number given by the shell model of the nucleus. We all know what is a magic number. So if a nucleus has certain numbers like 2, 8, 20, 50, 82, 126, those nucleus are found to have a greater stability. So those numbers we call it as a magic numbers. So the reason for the greater stability for the nucleus having the magic number was not given by the semi-empirical mass formula, and it accounted for the heavier binding energy of the heavier nucleus, and it did not clearly explain the binding energy of the lighter nuclei. As per the semi-empirical mass formula, if it is a lighter nucleus, there will be a more surface energy, then the binding energy will be very less. But when you taking into the account of the helium nucleus, it is a highly stable nucleus. So all these explanations were not clearly given by this mass formula, and this did not take into account of the internal structure of the nucleus. So whereas the shell model and the other model explains everything in terms of they include the internal structure of the nucleus. So these are some of the demerits of the semi-empirical mass formula.